In this section, we'll compare LoRA and QLoRA, two popular ways to fine-tune large language models efficiently. LoRA keeps the base model frozen and learns small adapter weights, which cuts training cost. QLoRA goes a step further by quantizing the base model, so you use even less memory while keeping strong performance. Understanding when to use each one is also a common AI engineer interview topic. The core question isn't whether you can define these methods from memory. Employers want to know if you understand the trade-off between adaptation efficiency and hardware efficiency, and whether you can choose the right approach for a real project with real constraints. Most importantly, they want proof that you can actually run it and make it work, not just talk about it in theory. Here's the cleanest way to separate these two. LoRA is about parameter-efficient fine-tuning. You keep the base model weights frozen and train small low-rank adapter layers instead. QLoRA still uses LoRa adapters, but adds 4-bit quantization to the base model, which makes training much more memory efficient. So both methods use adapters. The key difference is how the base model itself is represented during training. This slide shows the core idea behind LoRA. Instead of retraining the full model, we freeze the original weights and train small adapter matrices, usually called A and B. These low-rank updates are injected into the existing layers to capture the needed changes. Because only the adapters are trained, the number of trainable parameters drops dramatically, while the inference architecture stays exactly the same. Here's the architecture at a glance. QLoRA builds directly on LoRA by injecting small trainable adapter layers while keeping the original model weights frozen. The key difference is the systems layer. The base model is loaded in 4-bit precision using quantized linear modules and blockwise quantization. That cuts memory use dramatically. So even very large models, including 65 billion parameter models, can be fine-tuned on a single 48GB GPU. Here's the precision story at a glance. With LoRA, the base model stays in FP16 or BF16, and the adapters are also full precision. QLoRA keeps those adapters full precision too, but compresses the frozen base model down to 4-bit, typically NF4 or FP4. That gives much bigger memory savings, with a bit more implementation complexity. So the main bottleneck shifts from parameter count to available GPU memory. QLoRA was a major breakthrough because it made fine-tuning very large models dramatically more accessible. With QLoRA, even a 65 billion parameter model could be fine-tuned on a single 48GB GPU instead of requiring expensive multi-node infrastructure. The key was 4-bit quantization, specifically the NF4 format, which reduced memory usage while keeping performance remarkably close to traditional 16-bit fine-tuning. Here's the decision framework in practice. Choose based on hardware, not personal preference. If the model fits in available VRAM at FP16, LoRA is usually the easier option to understand, tune, and debug. For 7B to 13B models on a single A180GB, either approach can work well. But once you get into 30B plus models, especially on consumer GPUs, QLoRA is often the only practical choice. Here's the standard Hugging Face tooling stack we use. Transformers handles the core model workflow, loading models, tokenizing inputs, and defining the base architecture. PEFT adds efficient fine-tuning methods like adapters, LoRA, and QLoRA. Accelerate manages training across different devices and hardware setups. And bitsandbytes enables 4-bit and 8-bit quantization through specialized linear layers, helping us reduce memory use and train larger models more efficiently. Here's the core QLoRA configuration using bitsandbytes. We enable 4-bit loading to dramatically reduce memory use, while keeping the model practical to fine-tune. The quantization type is NF4, which works especially well because model weights are usually normally distributed. We also use bfloat16 for computation, balancing speed and stability. Finally, Double quantization compresses the quantization constants too, giving us even more memory savings with minimal quality loss. This slide shows how data moves during training in LoRa versus QLoRA. In standard LoRa, the input passes through a frozen FP16 base model, then through the low-rank adapter matrices A and B, where learning happens. In QLoRA, the base model is stored in 4-bit NF4 and dequantized to bfloat 16 on the fly for computation. In both cases, gradients flow through the LoRa adapters in full precision, keeping training efficient. Here are the trade-offs to know cold. LoRa is usually simpler to debug because there are no quantization artifacts, and it's easier to reason about gradient flow and adapter behavior. QLoRA lets you fit larger models on the same GPU by using 4-bit compression, but that comes with extra bitsandbytes dependencies and a bit more configuration overhead. In both cases, inference stays the same because adapters can be merged back into the base model for serving. Here are 5 interview questions to be ready for. First, what problem does LoRa solve? It freezes the main model weights and trains small low-rank adapters, which cuts the number of trainable parameters. Second, QLoRA goes further by quantizing the base model to 4-bit, reducing GPU memory. You'd choose between them based on hardware, model size, and simplicity. Be ready to mention transformers, PEFT, accelerate, and bitsandbytes, and to measure memory, stability, performance, and reproducibility. Interview prep isn't just about knowing your material. It's about knowing your audience. Different interviewers care about different layers of the stack, and recognizing that is a strong signal of maturity. With product-facing teams especially, start with trade-offs, user impact, and deployment outcomes. Don't lead with the math unless they ask for it. Show that you can connect technical decisions to real-world results. For the portfolio piece, build a clean side-by-side benchmark using the same task throughout. Something practical like customer support, legal summarization, or RAG answer tuning. Then run it twice, once with standard LoRa on an FP16 base model, and once with QLoRa using a 4-bit NF4 base. Compare 4 things clearly: memory use, number of trainable parameters, training throughput, and most importantly, final task quality. When presenting portfolio work, strong framing makes a big difference. Instead of saying, "I fine-tuned a model," describe the actual decision you were investigating. For example, I compared LoRa and QLoRa for a constrained deployment setting, measuring efficiency and quality trade-offs on a 7B model. Then make the setup concrete by showing which layers were adapted, the quantization configuration, the hardware you used, and why each method was the right choice. In your portfolio, make your resume show practical fine-tuning experience. In the skills section, highlight compute-aware fine-tuning, adapter methods, and quantization tools like bitsandbytes. In your projects, be specific. Name the model, the task, the hardware you used, the method you chose, and the trade-off between efficiency and quality. And in your tech stack, list the tools employers expect to see, like Hugging Face transformers, PEFT, accelerate, bitsandbytes, and PyTorch. What separates top candidates is practical judgment. They don't just repeat definitions or buzzwords. They talk clearly about trade-offs, like quality versus cost, latency, or risk. They understand the full tooling stack end to end, not just the model itself, but data, evaluation, deployment, and monitoring too. And most importantly, they bring evidence. Strong candidates show results with real numbers because in this work, measurable outcomes matter more than confident narratives. Here's the learning path I recommend. Start with LoRa so you really understand the core idea: frozen base weights, low rank updates, and how rank, alpha, and layer selection affect results. Then add QLoRA by learning 4-bit loading, NF4 versus FP4, double quantization, and the bitsandbytes setup. After that, run side-by-side experiments on the same task, measure all 4 metrics, and finally frame your interview story around constraints, method choice, and results. Here are the key takeaways. LoRA is all about parameter efficiency. You freeze the base model and train small adapter layers, which keeps fine-tuning simple, effective, and lightweight. QLoRA adds memory efficiency by combining LoRA with a 4-bit quantized base model, so you can work with much larger models on limited hardware. And together, these skills show the mix of modeling, systems, and product judgment that top AI teams really value.